this problem is for the I set up this problem like the concept problem for I hope that after you finish this problem, that is the circular motion. That's very easy to understand. Okay, and you may familiar with this type of problem from high school and from fundamental physics. Okay, so it is a circular motion. Actually, for circular motion, normally from high school and fundamental physics, you solve this type of problem in normal and tangential coordinate. Actually, okay, if you review it a little bit, okay, you may find that normally for circular motion, you will determine the normal acceleration. Okay, the acceleration that is 2y to the center of curvature, and also you determine the tangential acceleration. But actually, when you solve this type of problem, you may not mention that it is you use normal and tangential coordinate. Okay, but for the student normally familiar with x and y. Okay, and they may not know that for the circular motion that they solve in high school, normally they use normal and tangential coordinate system instead of x and y. Okay, so for this case, we will consider this problem that is a circular motion. The particle is travel in circular path with a constant velocity. Constant velocity means that the acceleration in tangential direction is become zero. Okay, and constant velocity around the circular path actually is represent the velocity that we have. Velocity vt is equal to 2 meters per second. Okay, for velocity that we have from that's given from the problems in curvilinear path. Normally, it is the tangential velocity. Okay, it's like you driving the car, riding the bicycle. Okay, normally you read the speed gauge of the car. The speed gauge always report the tangential velocity. It's not report velocity in x direction or in y direction or in normal direction. Actually, when you drive the car, okay, it has no velocity in normal direction. It has just only one component in normal and tangential. That is Vt. We have just only Vt. It has no Vn. Okay. Like when you imagine that you drive the car, you accelerate the car. So then it goes straight. It goes straight only. Okay. It's not go perpendicular to the directions of the car. Okay. If it not move like that. Okay. When you accelerate the car, it goes straight. It go to the direction that you would like to go. So normally the velocity for the curvilinear motion that's given from the problem represent velocity in tangential direction. And for this case, we set up the circular part of the circular radius of circular part is 4 meters. And we would like to determine the following values. First, we would like to determine the angular velocity. This is the actually you may familiar with when we have the velocity, the motion around the circular path. So velocity is constant, and it also have the angular velocity. Okay, and after that we will determine the velocity and acceleration in normal and tangential coordinate system. And after that we moving to the determine the velocity and acceleration in polar coordinate. And after that, finally, we will determine in x and y. Okay, I set up the x and y as the last because actually you're familiar with x and y. And I will show you that for these cases that we determine the circular motion, x and y is not suitable for this case. Okay, you will see. Okay, we can do it, but it's actually it's not suitable. So for this problem, okay, we will use this formula. Okay, we use this formula. It is curvilinear motion in X, Y, Z coordinate. Okay, and normal, tangential, and binormal coordinate. If it's a motion is in three-dimensional, it has the binormal also. But for this problem, we focus just only in plane. So then it has just only tangential and normal direction. And the last one is for cylindrical coordinate. But if we focus just only on the in plane motion, it is become just only polar coordinate. That is, the axis is it's just only r and theta, and this formula for that. Okay, starting with the first one, the first problem, we would like to determine the angular velocity. Okay, for the problem, we may note the coordinate. Okay, one thing that I would like you to remember that when we set up the coordinate system, okay, for x and y, we follow right hand rule. Okay, and for normal and tangential direction, okay, the tangent direction is always go tangent to the path. Tangent direction is always tangent to the path, and the positive direction is in the same of the motion. Okay, for the particles, if it goes to which direction, so then the positive one is in the same of the motion at that instant. Okay, and for the normal direction, it's always perpendicular to the tangential direction. But one thing that you have to remember that the normal direction is always toward to the center of curvature. Always toward to the center of curvature. So then for these cases, you see that the tangential direction is go this way. The tangential direction is go this way, right? Okay, this is tangential direction. Because the motion, we assume that we're moving counterclockwise. Okay, as a positive one. And the normal, it should be the perpendicular to tangential, right? Okay, but in which direction? Okay, the directions of normal is always toward to the center of curvature. So then the center of curve is over here. So then normal direction should be go this way. Okay, it's not go this way. It's not go this way. Okay, normal is not go this way because of the curve is go this direction. Okay, so when we set up the axis of normal, okay, do not confuse. Normal direction is always toward to the center of curve. Okay, so according to this, we can determine the angular velocity. We also have the relationship of velocity and angular velocity that you already know from the fundamental physics. And from this case, we can determine the angular velocity omega very easy from this relationship that we already know. The velocity is equal to 2 meters per second, and we have the radius is equal to 4 meters. So then it means that omega becomes 0.5 radian per second. This is the unit. Okay, and its the direction is counterclockwise for this case. Okay, then we're moving to the second one that we would like to determine the velocity and acceleration vector in normal and tangential coordinate system. Okay, so as I mentioned it before, so the axis of normal and tangential direction, it is a local coordinate. It's not constant. It's always change. Okay, for example, if the particle is moving around here, it's moving to this point. So what does it mean? It means that the tangential direction should be in this way. Okay, and normal is always toward to the center of curve. Okay, if the particle is moving to here, so then tangential direction is changed to be like this. and the normal direction is changed to be this instead. Okay, you understand? Okay, so then it's not like x and y that's they are fixed and not change direction. It's always to the left and upward. Okay, it's not changed. But normal and tangential directions and also r theta it's changed. It depends on its position. Okay. So for this case, we can write the velocity vector. Okay. Velocity vector in tangential coordinate is very easy because it has just only one component. So then we may find out velocity vector is because the velocity is constant from the problem that gives us that the particles moving along the circular path with a constant velocity. So then it means that it's like you drive the car in the circular path and maintain the velocity as a constant. So then the velocity is always become 2 at any point. Okay, at any point. Okay, and it is the vector become Vt just only one component is equal to 2t. T hat represent the unit vector in tangential direction. That is the first answer. That is the velocity vector. It's just really easy. This is equal to 2t. Okay, in normal and tangential direction. And for acceleration we have two components. Okay, the tangential direction, acceleration in tangential direction is depend on you increase the speed or not. At is the change in speed. Okay, it change in speed. So for this case, the problems give us that the particles moving along the circular path with constant acceleration. If it's constant velocity, so then it means that it's not change in speed. What does it mean? It means that At is become 0 for this case. But when to maintain the motion in circular path, it's required an, and it's used to change direction. We have an to change the directions of the particle along the path. Okay, and we already know that an is determined from omega square r or v square over r. So then for this case, we have an equal to 1 meter per sec square. Okay, 1 meter per sec square. And the direction is in normal direction, is in positive normal direction. So then the acceleration vector for normal and tangential coordinates become 1 n. Okay, because we have just leave 1. Okay, so then that's all for the velocity and acceleration in normal and tangential coordinate system. You see that when we are working out for the circular motion, you see that the motion derived in normal and tangential coordinates is very simple. It's very simple. Okay, easy to derive. Okay, so then we're moving to next type of coordinate system. For next coordinate system, we working out with r theta, It's just a little bit different from normal and tangential coordinate. And we compare with this. Okay, for this case, the polar coordinate system is r theta, but the directions of r theta it's not like the normal and tangential. Okay, for r, you will see that this is the center of curve. Okay, and the particle is over here. So then r represent the direction from the origin to the particle that for this case, it means that should be go outside. Is the direction is come from the center of curve to the particle. So you will see that R and normal is opposite direction for this case. And for theta is perpendicular to R and it's moving same direction of the rotation angle. Okay, so then V theta for this case is in this direction. And for this case is matched to the same direction as the tangential direction, just only for this case. So according to this, we use the formula for polar coordinate system that we already know for the formula. I will back to formula. Okay. We use this formula. In this case, we use this formula. Okay. So according to velocity, okay, for velocity of the circular part in polar coordinate, it has two components, VR and V theta. VR and V theta. VR represent R dot. V theta is R theta dot. Okay, but because R is constant, so then it means that R dot is become 0. So then you will find that the velocity become just only one component that is in theta direction. It is in theta direction. It's become and the magnitude is become only 2 because it's omega r, right? Okay. So then if you compare with the normal and tangential direction, it is the same as 2t, right? Okay. So then you will see that for this case, just only this case, u theta, that is a unit normal vector in theta direction, is the same direction of tangential direction. So then it is the same vector, right? Okay. When we're moving to the acceleration in polar coordinate, we use the formula again. Okay. And we will just starting with the derive for the derivative term for each. Okay. According to the constant of R, constant of radius. Okay. So then the term is reduced. Okay. And you found out the acceleration for this case in polar coordinate system. We have the acceleration just only one component, same as the previous one in normal and tangential coordinate. Because the particles moving with constant velocity, right? Okay. So then r dot dot is become 0. Okay. And we have just only components. And for theta components, you see that r is constant, but theta dot dot is become 0 because theta dot is 0.5 is constant already. So then theta dot dot is become 0. And for the last term, okay, r dot is 0 because r is constant and theta dot we already have, but for this term it's become 0. So in the same manner, we have the acceleration just only one component in r direction, but it is, if you consider the magnitude, it is equal to -1. Why is -1? Because the positive direction of r is go out from the center of curve. But for this case, it is the normal acceleration, right? It is the acceleration that try to change the directions of the particle to move in the curve. So then the directions of this acceleration is toward to the center of curve. Okay. If we compare with the acceleration in normal and tangential coordinate, we will find out this equal to this, right? Okay. So then it's negative. mean that it's opposite in R direction, that is go out from the center of curve, but for this case it is in positive normal instead. Okay. So that is for the last one. Okay. If we solve this in X and Y coordinate system, you see that we have to set up X and Y axis. And we starting with the position vector. Position vector is R in X and Y. So then for this case, position vector is R cosine theta I plus R sine theta J. So then if we would like to determine the velocity, we have to take derivative of this. Okay, so you will see that we can do it, but the formula is maybe not convenient to solve, right? It's stuck in X and Y, in I and J direction, and we obtain the velocity vector is become V is equal to minus 2 sine theta I plus 2 cosine theta J. Okay, and you can determine the direction of this vector also. That is, it is the same directions of the tangential direction and also the theta direction. Okay, and after that, when you would like to determine the acceleration, you have to take the derivative to velocity function again, and you will obtain that. After you take the derivative, you will see that we have to working out with the many manipulation in mathematics, and after that we can conclude that the acceleration is equal to minus cosine theta I and minus sine theta J. Okay, that's the direction. It's the same direction to the positive normal and positive R. Okay, and then for the last problem, I would like you to understand it more by ask you to determine the magnitude of each vector, and for this case we use the vector in X and in Y to determine the magnitude, and you found out the magnitude of the velocity is become 2 meters per second because it is just only one velocity, right? For this case, it is just only one velocity in tangential direction only. Okay, and it is matched to the velocity in tangential direction. And for acceleration, for these cases, we have just only one also. It is the normal acceleration, and we found out the acceleration is the same. It is 1 meter per second square. That is, and you will see that it is matched to the total acceleration from normal and tangential direction and r theta coordinate system. That is just for, that's the end of this problem. I normally ask the student to solve this in order to and I hope that my student will understand better for why we have to select this type of coordinate system to solve some problem. Are you right? Okay, that should be complete for this problem.